Welcome to a major turning point in the course, Object-Oriented Programming, or OOP. Until now, we've used procedural programming, focusing on writing functions or procedures that operate on data. OOP is a different and powerful paradigm that structures programs around objects, which are essentially real-world entities. 1. What is object-oriented programming? OOP is a method of designing programs using concepts like classes and objects. Instead of viewing a program as a sequence of steps, we view it as a collection of interacting objects. Think of a car. It's an object with attributes like color and speed, and actions like accelerate and brake. 2. Why is OOP important? The shift to OOP offers several key advantages for large software projects. Firstly, it offers modularity by grouping related data and functions together. Secondly, it provides reusability because we can create new objects from existing classes. Thirdly, it offers maintainability, making code easier to update and debug because changes in one object are less likely to affect others. 3. Procedural versus object-oriented. In procedural code, data and functions are separate. You pass data to a function to operate on it. In OOP, data and the functions that operate on that data are bundled together inside an object. This creates self-contained entities that accurately model real-world concepts. To summarize, OOP is not just a coding style, it's a way of thinking about program architecture. It's essential for working with frameworks and building scalable applications. These 4 principles, encapsulation, abstraction, inheritance, and polymorphism, form the foundation of OOP. Join me in Lecture 16.02, the 4 OOP principles. See you there. Welcome back. To grasp object-oriented programming, we need to understand its 4 foundational pillars. These principles guide how we design our software, making it robust, flexible, and scalable. They are encapsulation, abstraction, inheritance, and polymorphism. 1. Encapsulation. This principle is about bundling data and the methods that operate on that data into a single unit, which is typically a class. It also means restricting direct access to some of the object's components. Think of a smartphone. All its complex components and operations are packaged inside a single case, and you only interact with it through predefined buttons and the screen. Encapsulation protects the data from accidental outside modification. 2. Abstraction. Abstraction focuses on showing only essential information to the user and hiding the complex implementation details. When you drive a car, you use the steering wheel and pedals. You don't need to know the detailed mechanics of the engine to drive. Abstraction simplifies the interface and reduces complexity for the user. 3. Inheritance. This is the mechanism that allows a new class, called a child or subclass, to inherit the attributes and methods of an existing class, called a parent or superclass. For example, a car class and a truck class can both inherit common properties like color and speed from a general vehicle class. This promotes code reuse and establishes a logical hierarchy. 4. Polymorphism. The term means many forms. It refers to the ability of an object to take on many forms, or more practically, the ability of different objects to respond differently to the same method call. If both a dog object and a cat object have a make-sound method, calling make-sound on the dog produces a bark, while calling it on the cat produces a meow. The method is the same, but the behavior is different. To summarize, these 4 principles are the philosophical groundwork of OOP. Our next lecture 16.03, Classes and Objects. See you there. Welcome back. Before we start writing any OOP code, we must define the 2 fundamental concepts, classes, and objects. These terms are often used interchangeably, but they represent very distinct parts of the programming process. Understanding their relationship is crucial. 1. What is a class? A class is essentially a blueprint, a template, or a definition for creating objects. It doesn't actually exist in memory. It just defines what properties or attributes and what behaviors or methods an object of that class will have. For example, a dog class defines that all dogs have a color, attribute, and a bark method. 2. What is an object? An object is an instance of a class. It's a real, concrete entity that exists in memory. It holds the actual data specified by the class template. If the dog class is the blueprint, then Fido, a specific dog with brown color, is an object. You can create many different objects from a single class, like Fido, Max, and Daisy, each with its own unique attribute values. 3. Instantiation. Creating an object. The process of creating an object from a class is called instantiation. In Python, you typically instantiate an object by calling the class name as if it were a function, like my_dog equals dog with parentheses. My_dog is now an object or instance of the dog class. The class is the abstract template, and the object is the concrete variable you use in your code. To summarize, class defines, object realizes. Our next lecture 16.04. Create first class. See you there. Welcome back. Now that we understand the concepts of classes and objects, let's start writing our first object-oriented code in Python. We will define a simple class to represent a student, and then create individual student objects from this template. 1. Defining the class. To define a class in Python, we use the class keyword followed by the class name, which should always start with a capital letter and a colon. For our simple example, we use the pass keyword inside the class body. This means the class currently has no attributes or methods defined, but it is a valid blueprint that can be instantiated. 2. Creating objects. We create two objects, S1 and S2, by calling the class name followed by parentheses. This process is called instantiation. Both S1 and S2 are now independent instances of the student class. Printing the type of S1 confirms it is a student object. 3. Assigning and accessing attributes. Since we didn't define any attributes in the class, we can dynamically add them to the individual objects. We use the dot notation, such as S1 name, to set and retrieve attributes. Notice that S1 and S2 have completely independent name and ID attributes, demonstrating that they are distinct objects in memory. To summarize, we've created our first class and objects. However, dynamically assigning attributes like this is messy. We need a way to initialize the objects with data immediately upon creation. This is where constructors come in. Constructors allow us to pass data to an object when we create it, ensuring objects are properly initialized. Our next lecture 16.05. Use Parameterized Constructor. See you there. Welcome back. In the previous lecture, we manually assigned attributes to our objects, which is cumbersome and prone to errors. The Pythonic solution is to use a constructor, a special method called automatically when an object is instantiated. We will use a parameterized constructor to initialize our objects with values immediately upon creation. 1. Defining the constructor. In Python, the constructor is defined using the special method name, Def double underscore init double underscore. This method takes at least one argument. Self. Self is a reference to the instance of the class itself, and it must be the first parameter. Any other parameters like name and student underscore ID are the data we want to pass in. Inside the method, we use self to assign the incoming data to the object's attributes. 2. Instantiating with parameters. Now, when we create an object, we pass the values for name and student underscore ID directly inside the parentheses. The S1 equals student with parameters call automatically executes the double underscore init double underscore method, assigning Alice and 101 to the object's name and ID attributes respectively. This eliminates the need for manual assignment after creation and ensures the object is correctly initialized. 3. The role of self. Remember that self is not a keyword but a convention. It represents the instance on which the method is being called. It is necessary to use self inside the class to access or modify attributes belonging to the specific object, such as self name equals name. The self parameter is automatically passed by Python when you call the method. To summarize, the parameterized constructor is the standard way to create OOP objects with meaningful initial data. Our student objects now have data, but they can't do anything yet. Next, we will learn how to define an instance method to add behavior to our objects. Our next lecture 16:06. Define an instance method. See you there.
Welcome back. Our student objects currently hold data thanks to the constructor, but they can't perform any actions. In object-oriented programming, instance methods are the functions defined within a class that give objects their behavior. They allow the object to manipulate its own internal data. 1. Defining an instance method. An instance method looks exactly like a normal function defined within the class. Crucially, like the constructor, it must take self as its first parameter. This self parameter is how the method gains access to the specific object's attributes, like self.name and self.id. We define a method called get_info that returns a formatted string containing the object's data. 2. Calling the instance method. To call the method, we use the object's reference s1, followed by the dot notation, s1.get_info with parentheses. When you call it this way, Python automatically passes the s1 object as the self parameter to the method. The method then executes, uses the object's own data, and returns the result. 3. The difference between objects. If we create a second object, s2, and call the same get_info method, it will operate only on s2's data, returning Bob and 102. This highlights the core of OOP. The method is defined once in the class, but its behavior depends entirely on the unique data stored within the object that calls it. To summarize, we've now given our objects both data and behavior. However, accessing attributes directly, like s1.name equals something, breaks the principle of encapsulation. Our next lecture 16:07. Create getter and setter methods. See you there. Welcome back. In previous lectures, we accessed object data directly, like s1.name equals something. While Python allows this, it violates the OOP principle of encapsulation, which states that internal data should be protected. The standard solution is to use getter and setter methods to control how attributes are read and modified. 1. Defining the setter. A setter, or mutator, is a method used to modify an object's attribute. We define set_id, which takes the self-reference and the new _id value. The key advantage is that we can now add validation logic. Here we check if the new _id is a positive integer before actually assigning it to self.id. This protects our object's data integrity. 2. Defining the getter. A getter, or accessor, is a method used to retrieve an object's attribute. We define get_name. This method simply returns self.name. We can also use the getter to perform operations on the data before returning it, such as converting the name to uppercase, providing a layer of abstraction. 3. Using the getter and setter. We create a student object, s1. When we call s1.get_name, we receive the uppercase version demonstrating abstraction. When we call s1.set_id with 999, the assignment is successful. However, when we try to pass a negative number, the validation fails, and the ID remains unchanged. This shows how encapsulation protects the object's state. To summarize, getters and setters are vital for writing robust OOP code. They prevent direct attribute access and allow control over data. Our next lecture 16.08. Define instance methods. See you there. Welcome back. We've learned that instance methods define an object's behavior. In this lecture, we will define more instance methods in our student class to showcase how they can perform calculations, update an object's internal state, and take additional parameters. 1. Defining a calculation method. Instance methods can take parameters beyond self. We define calculate_fee, which takes course_credits. Inside the method, we perform a calculation, multiplying the given credits by a constant rate. Note that this method uses object data indirectly, but primarily relies on the external parameter to return a result. 2. Defining a state modification method. Instance methods are also used to change the object's internal state. We define celebrate_birthday. This method accesses self.age, increments it by 1, and then prints a message. This is a crucial concept. Methods are the gatekeepers that safely modify the object's internal attributes, which is the core of encapsulation. 3. Testing the methods. We create S1 with an initial age of 20. First, we call calculate_fee passing in 12 credits, and it correctly returns 600. Then, we call celebrate_birthday. Notice that after this call, the internal state s1.age has permanently changed from 20 to 21. To summarize, instance methods are essential for building functional objects. We have now learned constructors and instance methods. Constructors build and initialize an object, while methods define its capabilities. Understanding the distinction is vital for writing clean OOP code. Join me in Lecture 16.09, Methods versus Constructors. See you there. Welcome back. By now, you've worked with both the __init___ constructor and various instance methods. Although both are defined using def inside a class, their purpose, naming conventions, and execution timing are fundamentally different. Understanding this distinction is key to writing clean and correct object-oriented code. 1. Purpose and execution time. The primary purpose of the constructor is to initialize the object's state, giving it initial values. It runs automatically and only once, when you instantiate the object using student or similar. In contrast, an instance method defines the object's behavior, what it can do. It can be called any number of times manually after the object has been created. 2. Key differences in a table. Here is a table summarizing the key distinctions. Constructors always have the fixed name $_init $_. Methods have user-defined names, like get_info. Constructors are called automatically, while methods are called manually using dot notation. Constructors run only once, while methods can run multiple times. Finally, constructors implicitly return the new object, while methods can return any calculated value or nothing at all. 3. Practical example. In this example, when we execute s1 equals student Eve, the constructor runs immediately to set the name. The method introduced is not called until we explicitly tell the object to do so with s1.introduce. To summarize, the constructor is for setting up the object. Methods are for using the object. This completes our discussion on object-specific methods. Our next lecture 16.10. Define static field. See you there. Welcome back. Until now, every attribute we've defined, like the student's name, has been unique to each object. These are called instance variables. But what if we need a piece of data that is shared across all objects of the class? For this, we use a static field, also known as a class variable in Python. 1. Defining the static field. A static field is defined outside of any method, directly within the class body. Here, we define school_name equals Tech University. This variable belongs to the class itself, not any single object. Every student object we create will share this exact same value. The variable name inside the constructor remains an instance variable, unique to each object. 2. Accessing static fields. You can access a static field using either the object, like s1.school_name, or the class name, like student.school_name. Since this data belongs to the class, accessing it directly through the class name is the clear and recommended practice, making it obvious that you are dealing with shared data. 3. Static versus instance variables. When we change the static field using the class name, we see that the change is immediately reflected in all existing objects, S1 and S2. This confirms that they are sharing the exact same piece of memory. In contrast, changing S1.name would only affect S1, leaving S2.name unchanged. To summarize, static fields are used for shared data, like constants or properties relevant to the class as a whole. Next lecture 16.11. Count the number of objects. See you there. Welcome back. Okay, today we have a practical use for a static field is to keep a running count of how many objects have been created from a particular class. Since the static field is shared by all objects, it acts as a global counter for the entire class. Let's implement this feature in our student class. 1. Initializing the counter. First, we define the static field, object_count, directly in the class body and initialize it to 0. This variable belongs to the class. Next, we need to modify the constructor, the $_init $_ method, to increment this counter every time a new object is created. 2. Incrementing the counter. Inside the constructor, after initializing the instance variables, we increment the static field. Because object_count belongs to the class, we must access it using the class name student.object_count plus equals 1. We also define a simple get_count method to retrieve the total count easily. 3. Testing the counter. As we create 3 separate objects S1, S2, and S3, the constructor runs 3 times. Each time it runs, it increments the shared static field. When we finally print the student.object_count, the output is 3. We can also confirm this by calling the get_count method on any of the objects, as they all share the same counter value. To summarize, we have implemented a shared class counter, which is a key concept in OOP. Our next lecture 16.12. Create an inner class. See you there. Welcome back. We are now moving into more advanced OOP structures. Sometimes, a class is so closely related to another class that it only makes sense to define it inside the outer class. This nested definition is called an inner class. 1. Why use an inner class? Inner classes are used primarily for logical grouping. If a class, like address or engine, is tightly coupled and specific to only one other class, like person or car, it's best to nest it. This improves code organization and readability by keeping related components together. 2. Defining the inner class. We define the laptop class directly inside the student class. The laptop class is completely normal with its own constructor and method. This structure suggests that a laptop is conceptually part of a student record, though technically, the 2 classes remain independent until we link them via instantiation. 3. Accessing and instantiating. To instantiate the inner class laptop from outside the student class, we must use the dot notation, student, laptop, followed by the parentheses and arguments. This creates a separate laptop object, which we store in the laptop_obj variable. We can then call its method show_specs. 4. Linking inner object to outer object. There is the approach is to instantiate the inner class inside the outer class's constructor. The outer constructor takes all necessary parameters and creates the inner object, storing it as an attribute, self.laptop. When calling the constructor inside the outer class, we use self.laptop. To summarize, inner classes help organize related components. This concludes our dedicated coverage of Python's class features. Garbage collection is Python's automatic memory management system that reclaims space used by defunct objects. Join me in Lecture 16.13, Garbage Collection. See you there. Welcome back. As we create objects in Python, we allocate memory. But what happens to that memory when an object is no longer needed? Unlike languages like C, Python handles this automatically using a process called garbage collection. This lecture introduces this fundamental behind-the-scenes memory management system. 1. What is garbage collection? Garbage collection, or GC, is Python's automatic way of reclaiming memory used by objects that are no longer accessible or in use by the program. An object that is no longer referenced is considered garbage. GC sweeps up this garbage, returning the memory space to the system so it can be used for new objects. 2. Python's primary GC mechanism, reference counting. Python's core garbage collection technique is reference counting. Every object in Python has a reference count, which tracks the number of pointers or variables currently pointing to that object. When an object is created, its count is 1. When a variable is assigned to it, the count increases. When a variable goes out of scope or is set to none, the count decreases. 3. How reference counting triggers deletion. Let's look at a quick example. When we define a equals list 10, 20, the reference count is 1. When we set b equals a, the count increases to 2. When a is set to none, the count drops to 1. When b is set to none, the count drops to 0. At this precise moment, the object is considered unreachable, and the Python runtime immediately destroys the object and frees the memory. To summarize, reference counting makes memory management very efficient in most scenarios. However, sometimes we need more control. Our next lecture 16.14, GC methods. See you there. Welcome back. While Python's reference counting is efficient, it has a limitation. It cannot deal with circular references, where two or more objects refer to each other. To handle these rare but important cases, Python uses a secondary generational garbage collector, which we can interact with using the standard library GC module. 1. Importing and enabling GC. To use the garbage collector's methods, we first need to import GC. By default, garbage collection is enabled. You can check its status using gc.isEnabled, while you can manually disable or enable it. 2. Forcing garbage collection. The method gc.collect manually triggers a collection run immediately. It forces Python to look for unreachable objects, primarily those involved in circular references. This method returns the number of objects successfully collected. You may use this function for debugging memory issues or for performance optimization in resource-intensive sections of your code. 3. Inspecting reference count. While not directly in the GC module, the sys.getRefCount function is crucial for understanding how reference counting works. It returns the current number of references to an object. Note that it will always show a count 1 higher than expected, because passing the object to getRefCount temporarily adds 1 reference itself. To summarize, Python's garbage collector usually runs automatically, but the GC module provides manual controls and inspection tools. Before an object is collected, there's one last chance to perform cleanup operations. This is done using a destructor which runs just before the object is destroyed. The destructor, defined by the __del__ method, is the final method called on an object before it is fully destroyed, making it ideal for final cleanup tasks. Join me in lecture 16.15. Use Destructor. See you there. Welcome back. We've discussed the constructor, which is called when an object is created. Python also provides a mechanism for performing final actions just before an object is destroyed and its memory is reclaimed by the garbage collector. This mechanism is called the destructor, defined by the special method __del__. 1. Defining the destructor. The destructor is defined using the special method name def__del__. It takes only this self argument. We use a class called resourceHandler to illustrate. In the constructor, we open a file which is a system resource. In the destructor, we safely close that file using self.file.close. This is the place for cleanup tasks like closing database connections or releasing external resources. 2. When the destructor executes, we create an object R1, and the constructor runs immediately. Unlike a regular method, you almost never call the destructor manually. It is automatically called by Python when the object's reference count drops to 0. In this case, we manually use the del keyword to remove the reference R1, causing the object to be garbage collected, and the destructor to run, printing file closed. Object destroyed. 3. The automatic nature of deletion. We can also see the destructor run automatically. Inside the function func, the object R2 is created. When the function finishes executing, the local variable R2 goes out of scope. Its reference count drops to 0, and the destructor runs automatically without the need for the del keyword. To summarize, the destructor gives us one last chance to clean up system resources. With this knowledge, we conclude our learning about individual OP concepts. Okay, our next lecture 16.16, Patient Clinical's Use Case. See you there. Welcome to the final lecture of the OP section. We've learned many individual concepts: classes, objects, constructors, methods, and static fields. Now, let's bring them together to build a practical use case, modeling patient clinicals. 1. Defining the patient class. We start with the patient class. We immediately define a static field, patient_count, initialize to 0, and increment it within the parameterized constructor. The constructor also initializes instance variables for name, weight, and height. This sets up the data and the object counter. 2. Adding instance methods. We add 3 instance methods, all taking self. First, calculate_BMI is a calculation method that uses self.weight and self.height to return the BMI value. Second, update_weight modifies the internal state of the object. Third, display_report aggregates information, internally calling calculate_BMI to generate a comprehensive output. 3. Testing the use case. We instantiate 2 patient objects, P1 and P2. The static counter correctly shows 2. We call P1.display_report, which shows the initial BMI. Then we call the state modification method, update_weight, which changes P1's internal weight. Finally, calling display_report again shows the updated, higher BMI. This demonstrates the life cycle of an object, from creation and initialization to state modification and behavior execution. To summarize, congratulations! You've built your first end-to-end OP model, applying the fundamental concepts we've learned. Okay, we are going to the next section, encapsulation, next lecture 17.01. Introduction. See you there.